Hopefully you're now proficient at taking points on the normalized impedance plane and transforming them to locations on the complex gamma plane. Points like short circuit, or an open circuit, or a matched load, or a matched impedance, or a matched reactance. And of course we've also taken contours of constant resistance, vertical contours on the normalized impedance plane, or contours of constant reactance, horizontal contours on the normalized complex impedance plane, and transform them onto the complex gamma plane. And we see that that transformation creates circles on the complex gamma plane, contours which become circular, whose radius and location depend on the value of the constant resistance contours or the constant reactance contours. Now we're going to take it a step further. Instead of transforming a point from the complex impedance plane, the normalized plane, onto the complex gamma plane, or a contour from the normalized impedance plane and transform it onto the complex gamma plane, we're going to take whole regions from the complex normalized impedance plane and transform them onto the complex gamma plane. Whole areas of certain characteristic, all the points which satisfy some inequality constraint, and transform them onto the complex gamma plane and see what kind of resulting region appears in that situation. So let's look at this. What we're going to do is divide up the complex impedance plane, the normalized plane, into four regions. We can think of these as, four kingdoms, or four states, or four provinces, or four commonwealths, each with a boundary associated with them, or maybe two boundaries associated with it, and define them based on something to do with their impedance, either the real part or the imaginary part, the resistance or the reactance. So the first way we're going to do this is divide up our complex normalized plane in terms of resistance, the real part of the impedance. And to do this, we're going to draw three boundaries. First, we're going to draw a boundary which includes the all the impedance values whose real part is equal to 1. All the normalized impedance, therefore, whose resistance is equal to 1, corresponding to resistance equal to the characteristic impedance, Z0. We're going to draw a second boundary, and in this boundary, it's defined by the vertical contour R equal to 0. All of the locations on the normalized impedance plane where the resistance, the real part, is equal to 0. And of course we know this lies right on the vertical axis, on the imaginary axis of the normalized impedance plane. We're going to take a third boundary and draw this, and this is all the normalized impedances whose real part, the resistive part, is equal to -1, a vertical contour. Between these three boundaries, we're going to define a total of 4 regions. The first region is the region of all impedances, normalized impedances on the normalized impedance plane, whose real part is greater than 1. Imaginary part, of course, could be anything, but the real part is greater than 1. And of course, all those points lie to the right side of that boundary of R equal to 1. Then we're going to define a second region, and this consists of all the impedance points whose resistive value is between 0 and +1. In this case, this region has 2 boundaries on either side. A third region, which consists of all impedances whose real part has a value between -1 and 0. And finally, a fourth region, which consists of the remainder of the complex impedance plane, the normalized impedance plane, and that is all points that represent impedances whose real part is less than a value of -1. Notice for all 4 of these regions that they extend to infinity as we move up. As we move up, the reactive part of the impedances increase, and of course the reactive parts can increase to infinity. The boundaries of these regions are not defined at all by the reactive components, and so they must include all values from minus infinity to plus infinity. And of course then if we move downward, likewise all four of these regions will extend downward to infinity to include impedances whose reactance approach minus infinity. On the right side, the red region here, likewise, will be infinite as we move to the right. It will include the value of resistance that has a plus infinity because, of course, r equal to infinity is greater than r equal to 1, so it is included in this region. Similarly, as we move far to the left, it will include an impedance whose real part is equal to minus infinity because minus infinity is clearly equal to minus 1. If we look at the top part of these four regions, above the horizontal axis, we find that those four regions, those parts of the four regions, I should say, are residing in the inductive region of the complex impedance plane. The inductive region being the regions where the reactive component is positive or inductive. Likewise, each of these four regions include a portion of it, half of it, which reside in the lower half of the impedance plane, below the real axis, below the horizontal axis. And this includes, of course, all the impedances whose reactive component is negative. In other words, the reactance is capacitive, so they are in the capacitive region. If we look at the right two regions, where the resistance is greater than 0, of course, by definition, these regions reside entirely in the valid region of the impedance plane, where the real part is greater than 0. And of course, that means the left two regions, the green region and the purple region, those regions reside in the invalid region of the complex impedance plane. And so if we look at each of these four regions, we find that they reside entirely in the valid region for two of them, or the invalid region for the other two. But all four reside partially in the capacitive region, or the capacitive region, or reside in the inductive region, in the top half of the impedance plane. They span the boundary between the inductive and the capacitive region, because that boundary, of course, is the real axis. The horizontal axis of the complex impedance plane. All right, what we're going to do now is try to map these four regions onto the complex gamma plane. And that sounds like it might be fairly difficult, but it's really not too hard. All we have to do is really go through and map the boundaries between the region. Go through and map a contour, a vertical contour of r equal to -1. All the impedances whose real part are equal to -1. And of course, we've done that with the Smith chart. We looked at those mappings. We take this vertical contour and it will map into a contour that is circular on the complex gamma plane. We know what the center of that circle is going to be. We know what the radius of that circle is going to be. Likewise, we can map the vertical contour r equal to 0, all the impedances that are in fact purely imaginary, and map that onto the complex gamma plane. Once again, it'll be a circle. We know exactly where the center and radius of that is. In this case, of course, we know that will be the unit circle. And then finally, we map our third boundary, a vertical contour of all the impedances that have a real part equal to +1, and that will map onto a circle with a radius and a center. The regions that we have, for example, this blue region, is defined as all the points that reside between the two boundaries, r equals 0 and r equal to +1. Once we map those two boundaries onto the complex gamma plane, we'll likewise find that that same region will reside between those two boundaries. And by doing so, we can define each of the four regions here on the complex impedance plane we can define them on the complex gamma plane. But of course, they're not going to look like this sort of rectangular region that we have, because the mappings are circular of our straight boundaries, horizontal and vertical, onto the complex gamma plane. We find that these regions are going to be more interesting in their geography. So here are those mappings. Again, we go through and we know that the mapping of the vertical contour in the normalized impedance plane of r is equal to 0 maps onto the unit circle in the complex gamma plane. R equal to 0 means that the impedances are purely reactive, purely imaginary, and we know that maps to a circle whose magnitude of all points, whose magnitude of gamma is equal to 1. We also know now that the vertical contour of r equal to 1, that vertical contour in the normalized impedance plane will map to a circle on the complex gamma plane, which is this blue circle here. That circle, that contour, intersects the open circuit, as all of our contours do, but also intersects the origin of the complex gamma plane. And that's because the origin of the complex gamma plane is the matched impedance, a real value of 1 and imaginary part of 0. And the contour, therefore, of r equal to 1 includes that point and must intersect that point. So the impedance that maps to the center of the complex gamma plane is an impedance of r equal to 1 and x equal to 0. Finally, for our last boundary, we have the boundary r equal to -1, this green boundary here. And that's kind of a strange boundary. If you recall, we talked about those mappings. It doesn't look like a circle, of course. It looks like a vertical contour. But remember, this was a circle whose radius exploded to infinity. And so it's a circle so large that its curvature cannot be detected. It looks like a vertical contour, a straight line. That forms the last of our 3 boundaries. And the 4 regions, then, we can determine their mapping onto the complex gamma plane by simply looking at the region between the 2 boundaries that define them. And so we have a situation now where the purple region, r is equal to r is less than -1, is over here on the right side. The region where r is greater than +1 is inside this blue circle, this red region. The region where the resistance is between 0 and 1 is the blue region here. That's inside of the unit circle, but outside of the red region. And then finally, the region which is all impedances whose resistance are between 0 and -1 lie outside of the unit circle in this green region. It's interesting to note, we pointed out for the complex impedance plane that each of these 4 regions now have a portion that resides in the inductive region and a portion that resides in the capacitive region. And remember, the inductive region on the complex impedance plane is that entire region above the horizontal axis, above the real axis. Likewise, the inductive region on the complex gamma plane is the region above the horizontal axis, above the real axis of gamma. And of course, then the capacitive region is below that axis. And what we find is for each of these regions, just like in the complex impedance plane, the normalized impedance plane, each region has a portion above and below that axis, a portion in the inductive region and in the capacitive region. The green region, that's true. The blue region, that is true. The red region, that is true. And of course, then the purple region, that is true. Likewise, we saw on the complex impedance plane, the normalized impedance plane, that 2 of the regions lie completely in the validity region, or the valid region, I should say, to the right side of the vertical axis. And therefore, those 2 regions must reside likewise entirely in the valid region of the complex gamma plane. Valid region of the complex gamma plane is the unit circle, and what we find are those two regions, in fact, do reside completely in that unit circle. R greater than 1 is inside completely the unit circle, and the remainder of the region inside the unit circle is for the blue region, where R is between 0 and 1. The other two regions, where the resistive value of the impedance is somewhere between 0 and -1. That's the green region, and clearly that's outside of the unit circle. It's in the invalid region. And finally, all the impedances whose normalized resistance is less than -1, likewise in this purple region, lie outside of the validity region. So the mappings all make sense based on what we know and understand about the characteristics of each region, both in the complex impedance plane, the normalized plane, and also the normalized impedance plane, and also on the complex gamma plane. Now we're going to divide up the complex impedance plane, the normalized impedance plane, differently than we did before. In this case, we're going to use reactance as the criteria for segregating the region into 4 different regions. We're going to apply or define 3 different boundaries. In this case, the boundary, the contour, which is all impedances, normalized impedances, whose normalized reactance is equal to 1, a horizontal contour in the normalized impedance plane. A second boundary, it's hard to read here, but that is the boundary where the reactances have a normalized impedance equal to 0. And of course, this resides on the horizontal axis, on the real axis of the normalized impedance plane. And finally, a third boundary, which is all normalized impedances whose normalized reactance is equal to -1. They form a locus of points, which is this horizontal line on the complex impedance plane. Between those 3 boundaries, we can define then 4 regions. The yellow region, where all of the normalized reactances are greater than +1. The orange region, where the normalized reactances are between 0 and 1. The blue region, where the normalized reactance is between 0 and -1. And finally, this pink region, where the normalized reactance is less than -1. This case, if we look at these regions, they're sort of the dual of what we had earlier when we defined our regions based on resistance. In this case, we find that each of the 4 regions have a portion which is in the valid region, to the right side of the normalized plane, and a portion which is in the invalid region, to the left side. And of course, this makes sense because we defined our regions based on reactance and reactance only. The resistance could be anything from 0 to +infinity or 0 to -infinity. As we move to the right, as the resistance increase, this yellow region, as will all of the 4 regions, increase to infinity as the resistance goes to infinity. But on the other side, as we move to the left, as we move westward, then the resistance values will become more and more negative and approach -infinity. So half of each of the 4 regions reside in the valid region, where the resistance is positive, and the other half resides in the invalid region, where the resistance is negative. But let's look at the inductive region and the capacitive region. In this case, we find 2 regions, the yellow region and the orange region, reside completely in the inductive region, only in the inductive region, where the reactance is positive. The other 2 regions, the blue region and the yellow region, reside completely in the capacitive region, where the reactances are all negative. And that makes sense, again, based how we segregated these regions, and we divided them up based on their reactive values. Mapping these 4 regions from the normalized impedance plane onto the complex gamma plane, we get the result shown here. And again, we go through and we look at the 4 boundaries and how they map from the normalized impedance plane to the complex gamma plane. The boundary, which is x equal to 0, the horizontal axis on the normalized impedance plane, we know and have seen several times that it maps onto the horizontal axis of the complex gamma plane, the axis where the the imaginary part of gamma is equal to 0. The horizontal contour x equal to 1, all the impedances whose normalized reactance is equal to 1, it maps to a circle on the complex gamma plane that is shown here, and likewise the horizontal contour x equal to -1 on the normalized impedance plane will map onto a contour which is circular on the complex gamma plane, as shown here, the green circle. We just go through and identify the regions between these boundaries to see how the four regions that we stacked up in the normalized impedance plane, how each of those regions map onto the complex gamma plane. And what we find is the distinction between inductive region and capacitive region, between valid region and invalid region, likewise holds true on the complex gamma plane as well. There were two regions in the complex impedance plane, the yellow region and the orange region, that lie above the horizontal axis and therefore lie completely in the inductive region of the complex impedance plane. Notice those two regions also lie completely in the inductive region of the complex gamma plane. The orange and yellow regions lie completely above the horizontal axis and thus in the inductive region. The other two regions in the normalized impedance plane lie below the horizontal axis and therefore in the capacitive region where the reactances are all negative, and we find that that is likewise true in the complex gamma plane. The capacitive region of the complex gamma plane is likewise the region below the horizontal axis, below the real axis, where all of the negative reactances map onto the complex gamma plane. So the blue region and this purple region lie below the horizontal axis in the capacitive region. The other artifact we saw in the normalized impedance plane was for each of these four regions, half of the region lie in the valid region where R is positive, and the other half lie in the invalid region where the resistance is negative. And so that must be true in the complex gamma plane, and it is true. We find for each of these four regions, there's a portion inside the unit circle, inside the valid region, and a portion outside the unit circle, in the invalid region. That's true for the yellow region, outside and inside, the orange region, outside and inside, the blue region, outside and inside, and then finally this pink region, outside and inside. If we combine the results of all of these mappings, four regions defined by their resistance and four regions defined by their reactance, combine them together, what we find that we have 16 different regions on the complex gamma plane, 16 different regions in our Smith chart. On the complex gamma plane, we have 16 regions, and therefore 8 regions, inside of the validity region on our Smith chart. And so we look at these four regions and we can define them, again, based on both their resistance and their reactance. This region here would be, for example, have a resistance that is less than 1, but of course greater than 0, and a reactance that is positive between 0 and 1. So 8 different regions on the Smith chart that we can identify. How is this useful? Well, certainly we can go through and we can look at a Smith chart and identify certain points on the Smith chart and understand what that impedance, what impedance maps to that point. We can look at the short circuit point and know the impedance is equal to 0. We can look at the green point over here and we know that impedance has a magnitude of infinity, an open circuit. We can look at this blue point and we know that location on our Smith chart. That location in our complex gamma plane corresponds to a matched impedance, one whose real part is 1 and imaginary part is 0. We likewise know that if we have a point on the Smith chart that is on the unit circle, on that purple circle there, we know that reactance, or that impedance rather, is purely reactive, and its resistance value is equal to 0. What about the other location, some arbitrary location in our Smith chart? How do we know what impedance that corresponds to? If we map that point on the complex gamma plane back to the normalized impedance, what impedance would it be? What would be the resistive component and the reactive component, the real and the imaginary component? Well, of course, that's the beauty of the Smith chart, is we can take that point and lift our pencil and see where the contours intersect, and we can determine the impedance that it corresponds to. We've mapped all of the rectilinear Cartesian contours of the normalized impedance plane onto the complex gamma plane, so we can immediately determine the corresponding impedance value for a specific value of gamma. But do we really need to go through and evaluate the crossings of these contours to have some idea of what that impedance is going to be? Or can we look at its general location and, without having to evaluate the specific contours, know kind of what the impedance value is? For example, we know if we have a point that's in the upper half of the Smith chart, we know that the reactance of that impedance, of the impedance that would map to that point, must be positive because it's in the inductive region. Conversely, if we have a point that is in the lower half of the Smith chart, we know the reactance is going to be negative. The imaginary part of the impedance that maps to that point on the complex gamma plane must have a negative value. If we look at a point inside that blue circle, we know that that value of gamma must be mapped from an impedance whose resistive part is greater than 1, whose resistance is greater numerically than the characteristic impedance Z0, in other words. And of course then, if it's outside of the blue circle, we know that the resistive value is somewhere between 0 and 1 normalized. Finally, we can look at two contours. This contour, which is the x equal to 1 contour, and we see that if it's to the right of that gold contour, we know the reactance will be greater than +1, and if it is to the left, it will be less than +1, between 0 and 1. The green contour, if we're over here, we know the reactance is going to be less than -1, and then on the left side of that green reactance, it'll be somewhere between 0 and -1. And so putting all these pieces together, we can sort of go through and take any arbitrary point on the Smith chart and have some understanding of kind of what the impedance is going to be that resulted in that mapping. If we were here, for example, in this region, we would immediately know that the corresponding impedance has a resistive value that's greater than 1 and a reactive value which is positive, but one that is less than the value of 1. And good microwave engineers know their Smith chart geography. If they have a point in the Smith chart in that complex gamma plane, just by its location, without having to go and specifically look at the contours, just by its general location, they have a pretty good idea of the impedance that matches to it. Is the resistance big compared to 1 or small compared to 1? Is it positive, or is the reactance positive, or is the reactance negative? Is the reactance large and positive? Is the reactance small and positive? They can tell immediately by looking at that point without having to go through and more specifically looking at the contours underneath where they cross at that point.